And so welcome to our July 9th ME316 live lecture. We do have the homework that's due over chapter 12 content tomorrow. As a reminder, I did attach a PDF file to that one to show the specific problems for my edition 10 textbook, because I saw some students had maybe a different online version of that with different problems. And so that PDF is posted there. I guess, Jordan, did you have any questions over the homework?
No, I didn't.
All right, perfect. And I've been kind of slow on getting our lecture notes posted. Just busy with family and graduate thesis evaluations and defenses and all that stuff. And so I'll try to get caught up here after class today and get Monday's lecture notes posted, as well as the homework, the next homework over this combined loadings and failure theories. We will have one more lecture over that content after today, so I'm going to kind of look at that and see what that means for our next homework deadline with that last content coming in on Monday next week. This is going to be a shorter lecture looking at pressure vessels. So we'll have a short lecture for Friday. And I'll go ahead and share my screen. On Wednesday, we introduced the concept of failure theories, and now chapter 8 in your textbook, kind of stepping back a little bit, introduces you to combined loadings. And so our next homework set will be kind of a myriad of problems from chapter 8 onward that deal with combined loadings and failure theories. And the first case of combined loadings that we'll look at is just another loading type of condition, looking at thin-walled pressure vessels, which really applies when the thickness of the wall divided by the inner radius of that pressure vessel is less than about 0.1 is that critical ratio. If the thickness becomes greater than that, then you start to have a significant distribution of stress through the thickness, and you have to use thick-walled analysis. That is something that you'll look at in machine design, ME322, as it really fits one, to thick-walled pressure vessels, but also to press and shrink fits. The same relationships apply to that application from a machine design perspective. So what this is kind of more of an introduction to pressure vessels and looking at that most fundamental case of thin-walled pressure vessels. That really just assumes a normal stress through the thickness that is uniform in that. And once it becomes a thick wall, that's no longer the case. And so it underestimates the maximum by up to 5% if it meets this criteria of being less than 0.1. But that's close enough for design purposes. And the other thing to remember is that once you learn the thick-walled analysis, you could set that up in Maple MathCAD as a worksheet. You can apply the thick-walled analysis to thin-walled pressure vessels if you're concerned with the error associated with the thin-walled analysis. And also the analysis assumes a uniform pressure, which is pretty standard when you have pressurized gas contained in a pressure vessel. That's going to reach a common pressure inside there. And just a kind of reminder on pressure vessels, just what we're talking about. There are internally pressurized vessels that have a gas inside or a pressure inside. So common things would be just like your tire, propane tank, compressed gas cylinders would be internally pressurized. The International Space Station, those are all examples of internal pressure vessels that have a pressure inside. And then there are external pressure vessels where the pressure's outward pressing inward on the vessel. And so some examples of that, we have the supersonic wind tunnel in the mechanical engineering department there on the first floor. And there's that big tank that sits outside the north face of the building. For use of the supersonic wind tunnel, essentially what they do is they pull a vacuum in that big tank. And then when they're ready to run their test, they open a valve. And so the air from the HVAC system of the building rushes through that supersonic wind tunnel to fill that vacuum tank. And gives the ability then to look at shock waves and things like that across that fluid boundary through that supersonic wind tunnel. And so that time period when there is a vacuum in that tank, that's acting as an external pressure vessel with atmospheric pressure pressing down on that when that air is evacuated inside. A submarine would be another example of an external pressure vessel, submerged in a fluid deep underwater, has a lot of pressure acting on the outside, pressing it inward. Between the two of them, the external pressure vessels, typically failures in those systems is really just going to cause those things just to crumple inward. If that were ever to fail, the internal pressure vessels, those are very dangerous if they fail. It's essentially like a bomb going off if internal pressure vessel fails. And that's really kind of the reason ASME was formed back in the late 1800s. 1880 was when it initially formed, but that was kind of the time period that the steam power was being produced for both locomotion, train engines, and then also within factories. But they were experiencing failures in those types of boilers, and ASME was formed really to develop codes and standards to make sure those systems were safe. And as time went on, and what engineers do, always want to make things bigger, better, faster, they just needed to continually update the codes to make sure those systems remain safe as engineers really started to develop those further and further. And that's still an always ongoing area. We have alumni that work for Emerson Fisher. They make the large industrial valves for the nuclear power industry, the typical power plants, but those have to go through that whole ASME certification, and they still are pushing the envelope of what those codes and standards were meant for. And so they're in that process of evaluating and developing further codes and standards to make sure those things are designed safely. But that's what we're talking about when we're talking about internal pressure vessels and external pressure vessels. For the analysis that we're going to do here, we're going to focus specifically on internal pressure vessels. And then in machine design, when you look at thick-walled, that can be applied then to both externally pressurized and internally pressurized vessels. And so from a mechanics of material approach, that's really kind of the method that we use with Hibbler's textbook. We can look just essentially at a equilibrium summation of forces approach to estimate what the state of stress is. The machine design approach is more of a theory of elasticity, where you have the equation of stress as a function of that radial position. And so if we look at the mechanics of material approach and look at a cylindrical pressure vessel, essentially what we have is a cylindrical pressure vessel with two hemispherical caps. If we were to look at a stress element on that, you would have an axial stress, sigma A, along the length of the pressure vessel, and then a hoop stress, sigma H, acting tangential to that, or around the circumference. And so what we'll do is, if you were to look at, say, an isometric view, that's going to be along a curved surface, where you have your axial stress along the length and your hoop stress around that curved surface, representing that circular shape of the pressure vessel. The one good thing about that is pressure vessels are normally quite large. And so even though there's this curvature in there, as you go down to a smaller and smaller element, the curvature kind of is negligible when you're looking at that small element. So that curvature doesn't really come into play in terms of the stress analysis there. And then we'll look at various cutting planes. If we were to cut through AA, we can look at what the axial stress would be. And if we cut through the plane BB, we can see what the hoop stress would be. And so looking at that, again, we just have a pressure inside of here. And we look at a section normal to AA. Essentially what we'd have is our axial stress acting to the right for that material that we cut through along that cylindrical direction. And then we'd have a pressure times that cross-sectional area of the inside, that normal or projected area to that. So it'd just be the pressure times the area acting to the left. And even though, say you have a hemispherical cap here, the pressure always acts normal to that. So it's going to be acting at an angle, but it's also acting at an angle down here. And so those vertical components cancel one another out between that top and bottom of that hemispherical cap. And so the net effect, it's still that projected area of the pressure times that area of a circle that it's acting against. And so that simplifies things considerably, realizing that a lot of those forces cancel one another out. And so we can sum forces in the x direction to the right. Then you would have your axial stress, sigma A, times your cross-sectional area of your cylindrical portion, that tube essentially, minus P times the projected area of just pi r squared. And that's equal to 0. If we look at the cross-sectional area, it would be pi, r is that inner radius. So r plus t would give you the outer radius. So it'd be an r plus t quantity squared minus then an r squared would give you that cross-sectional area. And we can expand that out. The first quantity squared, r squared plus 2rt plus a t squared minus an r squared. So the r squareds will cancel with one another. And if t is really small, t squared is going to be really, really small. So that's going to be approximately equal to 0. And so this is part of the mechanics of material approach of just looking at that thickness over the radius being much less than 0.1. It allows us to neglect that thickness squared term so that we're left with 2RT. And then the cross-sectional area then would be 2 pi RT when we multiply pi through. And so the thin walled assumption again is if t is small, t squared is really small. And so we have sigma A times 2 pi RT minus the pressure times pi r squared is equal to 0. And when you cancel things on both sides, pi's will cancel and r will cancel with an r squared to leave us with an r on that side. And we can see that our axial stress is equal to the pressure times the radius. Again, that's the inner radius divided by 2 times the wall thickness. And so we have now a nice algebraic relationship for one of those stress components, the axial stress. And then this one does have some additional names for it. It acts along the length of the pressure vessel, so it's also referred to as the longitudinal stress. Now the next thing is if we section it along BB and look at just a differential element cut from that of length dx. And again, we're just kind of cutting through a section of it, so we're looking in the other hoop direction. We would have the radius, inner radius plus the thickness for half the height of this. And for that free body diagram, again, we'll have the pressure acting inward times that area and the hoop stress acting in the other direction. And so that should be a pressure times the area. I have it down in the equation here. But if we're summing forces, say this is in the y direction, now we'd have the sigma hoop times the cross-sectional area of the top and bottom sections minus the pressure times the area would be equal to 0. And so the cross-sectional area on this one would just be equal to the thickness times dx would give us the top half, and then times 2 would add in the bottom half. So the cross-sectional area would just be 2t times dx. And then the area, the internal area, would just be 2r times dx. It would give you the area, projected area of this rectangle. And so there again, we can plug those in and solve sigma h times 2t dx minus p times 2r dx is equal to 0. And we find that our hoop stress is equal to PR over T for that one. And if we remember back, axial stress was PR over 2T. And that means our hoop stress is twice as great as our axial stress for a cylindrical pressure vessel. This hoop stress also has a number of names associated with it. Since it acts tangent to the axial stress, it's also called the tangential stress. And then since it acts around the circumference of the pressure vessel, it's also referred to as the circumferential stress. So you'll hear those being used for this hoop stress as well. And so what does that mean in terms of the state of stress? We find that the hoop stress is twice as great as the axial stress. And so since that's twice as great, what you're normally going to find for a pressure vessel is that when it fails, it's going to split along the length of the pressure vessel due to the hoop stress pulling that apart. If you've ever left a soda can in your vehicle in the winter here in South Dakota, if it does split open, you'll see that acting vertically along the length of the pop can, how it fails. There's another time that we toured, I'm thinking it was the North Omaha power plant. and they were refurbishing the superheaters for the boiler. And they had a big section of the wall open so you could look in and see all the piping and everything in the superheated system. And you could see some of the pipes had failed, where there was a vertical failure along the length of the pipe, and it had opened up. And then another aspect of that is really trying to avoid that explosive nature of pressure vessel failing. And so with those, there is a leak before break design for pressure vessels where a crack is able to make it to the outer surface and release the contents of the gas before an explosive event occurs. And so that's something that I would always teach in machine design. I'm pretty sure Dr. Bruno covers that too. But that gets more into that concept of fracture mechanics and looking at the theory of elasticity approach for thick-walled pressure vessels, introducing that leak before break design for pressure vessels. I think as I talk through this stuff, as we move into the next couple weeks, I'll probably pull up some photos so I can show you those types of failures for pressure vessels. And then next up is a spherical pressure vessel. And what we find for that case is that in both directions, we end up with that similar axial stress loading component that is PR over 2T. If we were to go through and draw the free body diagrams the same. And so the interesting thing is then what we find with spherical pressure vessels is they don't have that large hoop stress component that the cylindrical pressure vessels see. And so for supercritical applications where you're trying to keep the stress levels down, a spherical pressure vessel can achieve that, but it's just more complicated to design a spherical pressure vessel and to manufacture that. And so that's why you tend to see cylindrical pressure vessels more. And so I guess special note is that when we look at this from a combined loading standpoint, in the absence of any other type of loading, your axial stress and your hoop stress are going to be the principal stresses acting along the plane of that surface. And then there's a third principal stress that occurs on the inner wall of the pressure vessel. That's equal to minus the pressure. So sigma 3 is equal to minus P. But when you look at the hoop stress, PR over T, again, R over T is going to be greater than 10 for a thin-walled case. So your hoop stress is at least 10 times greater than your pressure, and your axial stress is at least 5 times greater than your pressure. And so this sigma 3 does end up becoming somewhat insignificant in terms of, say, the von Mises stress. But it is something you still need to take into consideration because it will alter it just a little bit. It does become more important then for thin-walled pressure vessels as that pressure component becomes a greater contribution of the state of stress. Then from a practical standpoint, this for internal pressure vessels, you have that minus P on the inner wall, and then it goes to 0 at the outer wall when you're looking at just the gauge pressure. But the implication that has on failure is that you have a slightly greater state of stress on the inner wall of the pressure vessel than you do on the outer wall. And so failures will always originate on the inner wall of the pressure vessel and then extend outward to the outer wall. And so that is important in that leak before break design of pressure vessels, as you want that crack to be able to extend all the way through the wall of the pressure vessel so it can leak the contents before an explosive event occurs. In addition to that, you can have pressure relief valves designed into your system so that the pressure doesn't exceed a certain amount. It'll vent that off beforehand. You kind of have to be careful with that in terms of your application. Sometimes the gases that you're working with internal pressure vessels, mixing chemicals, that type of thing, just aren't friendly to the people in the area. And so you really have to be careful on what's the worst case outcome in terms of releasing gas that could be harmful to people, or an explosive event that can be harmful to people too. So there's lots of stuff to take into consideration there. But in terms of inspection, that can make it difficult to identify when failures are beginning to occur. And so they have different X-ray methods to identify those internal cracks. For other applications where it's a super large pressure vessel, they'll evacuate all the contents out of the pressure vessel, have people go in and visually inspect the inside of the pressure vessel to see if any cracks are forming and if they need to be repaired at all. And then we can just look at combined effects of axial and pressure loading. I think all the problems that you have out of chapter 8 with regard to pressure vessels, it's just a simple algebraic relationship, PR over 2T or PR over T. So I'm pretty sure you can handle the algebra part of that just for a basic pressure vessel. You can apply the failure theories with the state of stress, the 3 states of stress on the inner wall. And then when we start looking at combined effects, we could have, say, an axial loading and a pressure loading. This 5.9 comes from a different textbook, and the problem itself comes from a different textbook. But if we have a pressure vessel that's subjected to an axial force as well, here I'm going to use F for force instead of our capital P that we used back when we discussed axial loading, because we want to use the lowercase p for pressure. And so that'll help us avoid confusion there. But anytime you're dealing with combined effects, all you really need to use is superposition to combine then the axial stress component. If we have a pressure vessel, that's going to create our axial stress in the X direction and our hoop stress in the Y. But then a force added to that is going to combine and add an additional stress in the X direction. And so here we're given that we have a 3-foot inside diameter pressure vessel with a 0.375 inch wall thickness. And the pressure is equal to 300 PSI, which would be equal to a minus sigma 3, the stress on the inner wall of the pressure vessel. And what we're asked to find is the maximum force that can be applied to this at the same time as that pressure, if the maximum axial normal stress is 18 KSI. And so this is kind of a weirdly posed problem in that they're concerned about the maximum axial normal stress, which would really relate to, say, our maximum normal stress theory that we looked at on Wednesday, the one that we said was really kind of bad to use, as it does not capture ductile failure very well. But we can go ahead and solve this, and then I think I look at the von Mises. Maybe not. I think I just talk about it. That you could, oh yeah, here we go. I do look at von Mises as well. but we can look at that. And so for the analysis of this, then we really need to know what the axial stress and the hoop stress is based on this 300 PSI pressure. And then based on that, we can calculate what maximum force could be applied to reach that 18 KSI. And who knows, maybe we're dealing with a brittle material and they are concerned with that from a maximum axial stress standpoint. But from a pressure vessel standpoint, you'd never want to use a brittle material for a pressure vessel. Brittle materials fail without warning. That would be a bad thing for a pressure vessel. So our hoop stress is PR over T. Pressure is equal to 300 PSI. Our internal radius is 1.5 feet. And our wall thickness was 0.375 inches. And so we need to convert that feet to inches. And so we have 12 inches in a foot. And that'll work out as 14,400 PSI or 14.4 KSI for our hoop stress. Sigma axial is PR over 2T. And that's just equal to the hoop stress divided by 2. And so 7,200 PSI for that axial stress component from the pressure side of things. And so that shows you the two stress states caused by the pressure. And then the axial that we're concerned about is exceeding 18,000 KSI. And we have 7,200 or 18,000 PSI, and we have 7,200 PSI coming from the pressure side of things. And so that gives us 10,800 PSI that would be coming from the axial loading component of that. And so that axial portion would be 10,800 PSI, just force divided by the area. And we could use that approximation 2 pi over RT. Essentially, that's the circumference of the pressure vessel times the thickness is that approximation. And again, R is equal to the 1.5 feet. So 18 inches altogether, and the thickness is 0.375 inches. And that'll give a force of 458,000 pounds or 458 kip. And so that's really the answer to the problem, is that it could withstand a 458 kip force. In addition to that pressure, that would get it to just that point of 18,000 PSI for the axial stress. The interesting thing is both of those hoop stress and axial stress are tensile type stresses. And so you're kind of looking at that biaxial strengthening area where the von Mises failure envelope goes a little bit out from the maximum normal stress theory. And so what about von Mises with this load? Sigma is just 1 over the square root of 2 times the difference in all the stress components. So if we're all the way fully up to the 18 KSI and our sigma hoop is 14.4 KSI, we have those two terms, and then we have 14.4 minus sigma 3, which is a minus 0.3. And so that ends up being plus. And same thing for the last stress component. What we find is that the hoop stress, or sorry, the von Mises stress for this is 16.8 KSI. So even though we have a axial component that's 18 KSI, just based on that biaxial strengthening area, the equivalent uniaxial state of stress for von Mises is slightly lower at 16.8 KSI for that area. And so this is then more a parameter that you would want to use if you're dealing with a ductile material for a pressure vessel. If for some odd reason you had a brittle material in that roll, it would be the 18 KSI. That would be important from a failure standpoint. Does that make sense, Jordan?
Yeah.
Yep. Okay. And so that's just kind of a look at the pressure vessels and also kind of tying it into the failure theory discussion we had on Wednesday. You could also look at the elongation. How much does the pressure vessel stretch? And you could use Hooke's law, the full 3D version of that, to solve for that. So your strain in the X is 1 over E times quantity sigma X minus nu sigma Y plus sigma Z. And so sigma X is really your axial component, 18 KSI. Sigma Y is your Hooke component, and sigma Z would be your minus pressure. And so you just need to know what the Young's modulus is and the Poisson's ratio is for the material. And you could figure out what your strain in the X is. If you know what your length of your pressure vessel is, you can then calculate the displacement. And I've mentioned that before, just the pressure vessels running from the powerhouse for the hospital to the hospital has these long pipes interconnecting, but then they have flexible couplings at the end of those long pipe segments just to really allow that free expansion and contraction of the pipes as they are subjected to pressure changes and temperature changes, so that you don't build up a stress in the X direction. The strain in the X is fully allowed, and that, again, displacement would just be the strain times the length of that pipe. Then if you're looking at the transverse direction, that'd just be a change in diameter over the original diameter is equal to the same 1 over E sigma Y minus nu sigma X plus sigma Z. You could run that through as well. And we have another example problem. This one's about 2 pages, and then we'll be done for the day. I don't think we'll even need a break. So far, we introduced internal pressure vessels. We've looked at internal pressure vessels subjected to axial loading. And now we can look at a case of an internal pressure vessel subjected to both axial and torsional loadings. And so superposition still applies. And here we're given that we have a 50 millimeter diameter steel bar. I guess we're not dealing with pressures at all on this one. We're getting just more into that discussion of combined loadings in general. And so we could add a pressure to this, but for this one, it's just going to be an axial load and a torsional load that we're looking at for this example problem. And I'm doing the same thing again. I switched it to a force to define our force, so we don't get confused with the pressure thing again. So we're given a 50 millimeter diameter steel bar. So it's just circular, Young's modulus 200 gigapascals, Poisson's ratio equal to 0.3. It's subjected to a tensile load F and a torque T. And we have strain gauges placed on here, and the strain gauge A is reading 1,414 micrometer per meter. And strain gauge B is reading a minus 212 micrometer per meter. And they are orientated at 45 degrees from the X direction. And based on those strain readings, we want to then know what the force and the torque is that this circular bar is subjected to. And then 2, adding on there, what is then the corresponding von Mises stress from maximum distortion energy theory. And so this is a topic that we really haven't reviewed yet here in ME 316. This was kind of a topic that you looked at in ME 216. And so this is just applying that concept that you learned in ME 216 so that we can figure out what the loadings are on the object. And this is really handy. I assisted the formula team one time in looking at a torsion bar to transfer loading at the rear wheels. And we put a strain rosette on there so that we could measure the torque with strain gauges. And so it has that same concept. But when you look at the strain readings and that correlation to the state of strain at this point, we have strain of A is equal to strain of X cosine squared theta A plus strain of Y sine squared theta A plus a gamma XY sine theta A cosine theta A. And strain B is the same thing, except you're replacing theta B in there for those terms. And when we do that, counterclockwise is positive, so theta A is a 45 degrees and theta B is a minus 45 degrees. And the strain in the Y would just be equal to a minus nu strain in the X. And with that then, we know the Young's modulus and the Poisson's ratio. And so it breaks it down into 2 equations and 2 unknowns. We know strain of A, strain of B, so our unknowns would be strain in the X and gamma XY. And so we can plug then our values in for that and end up with 2 equations, 2 unknowns for strain in X, strain in the Y, and then solve for those. I ended up with a strain of X of 1,717.14 micron per meter and gamma XY of 1626 microradian. And so with those 2 strain components, the benefit of what we have here is it's a purely axial loading combined with a pure torsional loading. And so the 1D relationship applies for that strain in the Y direction. And the other torsional component is just going to result in a shearing strain. And so based on these strains that we're getting then, we can solve for the corresponding torque and the force that's applied. Let's see, we'll do the torque portion first. Looking at that stress element, then we have a stress in the axial direction and then a shear stress acting on that. And so that's what our stress element would look like. We know the Young's modulus and Poisson's ratio. And so with that, we can estimate what the shear modulus is, E over the quantity 2 times 1 plus nu would be equal to 76,923 megapascals for the shear modulus. And so that shear stress would equal to the shear modulus times the shearing strain that we just calculated. 1626 microradians is the same as 1626 times 10 to the minus 6 radians. Will give us a shear stress of 125 megapascals. And then the torque, remember shear stress is equal to TC over J. So just rearranging that, the torque would be equal to the shear stress times J over C. And we just solved the shear stress, 125 megapascals. J would be a pi d to the 4th over 32. And C would be 25 millimeters, the radius. Will give us, I simplified this in terms of units. The units that would come out would be in Newton millimeters. And then I simplified that down to 3.07 kilonewton meters. So I did skip a step there. I always recommend giving your answer in the units that would come out in, and then converting it. And I did the same thing for the stress in the axial direction. Again, since it's purely axial with that torsional component, that's not going to come into play for that axial direction. It'd just be the strain in the X times the Young's modulus. And so that's 1,717.14 times 10 to the minus 6th times the Young's modulus, 200,000 megapascals, will give us 343.428 megapascals. And the force then would be sigma times cross-sectional area. So stress times pi times diameter squared over 4. Again, this would have came out in terms of newtons. And so it'd be 674,000 newtons. And then I simplified it down to 674 kilonewtons. And so we have those two answers then for the torque and the force that would have caused that state of strain at that point. And then if you look at von Mises stress, again, our normal axial stress was 343.428 megapascals. Our shear stress is 125 megapascals. And if we look at von Mises stress, this is a common loading condition where you have a pure axial torsional loading. And so if we look at that from the actual state of stress, where we have our sigma x term, this would be sigma x, our sigma y and sigma z are 0. Tau is our tau xy, and tau xz and tau yz are both 0. This simplifies down pretty well. We'll have 2 sigma x squared coming from these two terms. So we have 2 sigma x squared plus a 6 tau x squared. And so we can pull a 2 out of that expression and take the square root. So we'd have the square root of 2 over the square root of 2. That'll cancel. And we'll be left within a sigma x squared plus a 3 tau xy squared within the parentheses here. And so for pure axial torsional loading, the equivalent state of stress is just what that axial stress component is squared plus 3 tau xy squared square root. And so that's a bit of a simplification from the bigger von Mises or maximum distortion energy theory. That simplifies out. And plugging those two values in there, we find that our equivalent uniaxial state of stress is 406 megapascals. And so that is it. That kind of covers that second example problem there, dealing with just a force, axial loading, and a torsional torque applied to it. No pressures at all on that one. And so that's really what combined loading entails, is really looking at all the states of stress, all the loadings that are applied, and looking at a specific point and what components of stress are caused at that point by all the different loading conditions. And so when we did the problems here today, it wasn't too difficult to keep track of those. But when you start dealing with like 3D space and situations where you have a bending moment, you have a torsion, torsional shear stresses applied, axial loadings, transverse shear stresses. It gets to be really confusing to try to keep track of those like we did here today. And so kind of the process that I've recommended is, I call it the accounting method for combined loading analysis. Basically just make a table of all your potential stress components and then look at critical locations that those are likely to combine to generate a worst case scenario, and then determine what components of stress are caused at each one of those locations. And then you're able to simply add and subtract those like components. Say you have multiple sigma X components, those can all be combined together algebraically. If you have different stress components, sigma X, sigma Y, tau XY, tau YZ, then you're having to use the failure theory to find your equivalent uniaxial state of stress. And so that's where we're heading on Monday, is looking at that accounting method for the combined loading so that we can keep track of all the different states of stress that are occurring. And so let's see, I guess, do you have any further questions, Jordan?
I don't think so.
All right. And so we'll call that good. I'll take a look at the homework assignment and looking at our discussion that we planned for Monday. I'll get that those lecture notes posted, and then I'll get the homework assignment posted and decide on a due date for that. But I'll do that here after I get this video posted to D2L. But we'll call that good. Yep.
Are we still expecting an exam next week towards the end?
Yeah, it's going to be in that time frame. We'll be close to getting this homework done. And so I can always release the exam and then make sure the due date is well after the homework has been graded and the solutions posted. So it'll be a similar format where I release that online and then you have a while to do that.
Okay.
But yeah, we'll call that good for today. Have a good weekend and we'll see you on Monday.
You too. See you on Monday.
Yep. Bye.